Hello guys, welcome back to my channel or Davig Structure Hub. So if you are a new subscriber, this is the channel for structural insight, and it is the #1 channel in Kenya and outside Kenya. And this is a place where you learn, build, and innovate. As I promised you last week, that this week I will start design of steel to BS 110, and without further ado, I want to start this topic due to request from many students who are sitting for exams this November. So I'm not just doing it for the purpose of passing exam, but I'm also doing it for those who are practicing structural engineering, so that you may get the concept and know how to design structural steel to BS 5950. And for your information, I have not completed reinforced concrete design, to BS 8110. So what I'm remaining with is, number one, this is staircase design. Number two, we have the double pad foundation. And number three, we have the ribbed slab design. So I will finish these three as I continue with the design of steel to BS 110. So stay tuned for that. So let's go back into today's topic, which is design of steel to BS 5950. So I want to begin by introduction. So under introduction, we will discuss the following subtopics. So number one, we have division of BS 5950. So number one, division of BS 5950. 5950, or parts of BS 5950, or parts. Then you have the number two. I will talk about concept used in steel design. Then number three, I will talk about structural steel and steel section. Structural steel and steel section. Number four, I will talk about symbols. Number five, I will talk about method of design in BS 5950 part 1. Methods of design in BS 5950 part 1. Then number six, I will talk about, so under this subtopic number 5, we'll discuss the following. We have the simple design. We have the rigid design, or continuous design. or a continuous design. So again, we have semi-rigid. Or semi-continuous design. And then you have number 6, material properties. Number 7, we have design consideration. So under design consideration, we will discuss about bending. We discuss about bending. We have shear. We have deflection. We have web buckling. And we have web bearing resistance. And then we have number 8. We'll discuss about strength classification. Then the last one, number 9, summary of design process. So after summary of design process, then we will be able to tackle an example, but not for today, maybe tomorrow or another day, probably tomorrow. So this is what we will discuss today. And remember, BS59 has been superseded by Eurocode, which is EN 1993. So after finishing this steel design to BS 5950, I will start Eurocode and you'll be able to know how to use the Eurocode for steel and the Eurocode for concrete. So stay tuned for that. So let's start by division of BS 5950. So we begin by division of BS 5950 or parts. So BS 5950 is divided into the following 9 parts. So it's divided into 9 parts. I will not write it on the board, but I will read it for you. So we have part 1, code of practice for design. So this is for roll and welded section. You have part 2, specification for material, fabrication and erection, roll and welded section. We have part 3, design in composite construction. This is section 3.1, code of practice for design of simple and continuous composite beams. We have part 4, code of practice for design of composite slabs with profiled steel sheeting. Part 5, code of practice for division of cold formed thin gauge section. We have part 6, code of practice for design of light profiled steel sheeting. We have part 7, specification for materials, fabrication and erection, cold formed section and sheeting. Then you have part 8, code of practice for fire resistance design. Part 9, code of practice for stressed skin design. So we will talk later about these parts in detail. So number 3, we have structural steel and sections. Structural steel and section. So the structural steel is manufactured in 3 basic grades. So manufactured in 3 basic grades. Number 1, we have S275. Number 2, S355. And then the last one, we have S460. So grade 460 is the strongest. So this one is the strongest. But the lower strength grade S275 is the most commonly used. So 275 is the most commonly, and remember this is the lowest grades. In structural application, S stand for structural, and the number indicates strength of the steel. This is the yield strength. Yield strength in Newton per millimeter square. Like that. The most commonly used section are universal beams, UBS, and universal column. So universal beams and universal column are a most commonly used section. Like that. The geometric property of these steel sections include the principal dimension have been tabulated in booklet entitled Structural Section to BS4, Part 1, 1993, and BSEN 156. So I want to now talk about symbols used in the design of steel to BS 5950. We have the symbols. So we have the geometric symbols. Geometric symbols. Because these symbols are of so many, I won't write them for you guys. So what I will do, you will learn them as we proceed with the design of steel to BS 5950. But know that we have geometric symbols. Then number 2, we have the bending symbols. You will see them in the design. Then number 3, we have compression symbols. Like that. Now, let's talk about design of steel to BS 5950 part 1. So remember I said that this BS 5950 is divided into 9 parts, and we want to start, or we want to talk in details about design of steel to BS 59 part 1. So under this, 3 methods of design are included in BS 5950 part 1. This is simple design, number 1. Number 2, rigid design, stock continuous design. And number 3, we have semi-rigid design or semi-continuous design. So number 1, we have simple design. So applies to structures in which the end connection between members are such that they cannot develop any significant restraints moments. So the structures may be considered pin jointed or the basics of the following assumption. So number 1, all beams are simply supported. All beams are simply supported. As you can see, a simply supported is a beam with 2 supports only, or a beam resting on 2 supports. B, all connections are designed to resist only resultant reaction at the appropriate eccentricity. And then D, columns are subjected to loads applied at the appropriate eccentricity. And we have the last one, which is D, resistance to sway is provided by either bracing, shear walls, or core walls. So that is all about simple design. So number 2, we talk about rigid design stroke continuous design. In this method, the structure is considered to be rigidly jointed such that it behaves as a continuous framework. Therefore, the connections must be capable of transmitting both forces and bending moments. Portal frames are designed in this manner using either elastic or plastic analysis. So this is an example of a portal frame. Like that. Now let's talk about the semi-rigid design, or sometimes it is called semi-continuous design. So this is number 3, like that. So this is a design based on experience and experiments which allows the joint in the structure to transmit some restraints moments. The design approach in BS 5950, now we are talking about the design approach in BS 5950, is based on limit state philosophy. Limit state is grouped under, we have A, ultimate limit state, or ULS, and this may be regarded as an ability to sustain any increase in load. The ultimate limit state, in ultimate limit state, there are conditions to be avoided, and they include strength. Conditions to be avoided include strength, stability, fracture due to fatigue, brittle, and brittle failure. So I will discuss them in detail. So I will begin by strength. So the individual structural element should be checked to ensure that they should not yield, buckle, or rupture under the influence of ultimate design load or forces and moments. Then we have number 2, stability. The building or structure framework as a whole should be checked to ensure that the applied load do not induce excessive sway or cause overturning. And then we have the fracture due to fatigue. Fracture due to fatigue. Fatigue failure could occur in a structure that is repeatedly subjected to rapid reversal of stress or application of cyclic loads. And then you have the brittle failure. Sudden failure should not occur. Sudden failure should not occur. So let's now talk about the serviceability limit state, or LSLS. So these are states that are undesirable. Example, we have deflection, corrosion, fire protection, vibration, and durability. The ultimate design load is given by 1.4 GK plus 1.6 QK. This is the same formula we have been using in the reinforced concrete design to BS 8110. So whereby GK is the dead load and QK is the live load. At serviceability limit state, the factor of safety is 1. So material properties for beams and column sections. The material thickness referred to in the table is taken as the flange thickness. So we have the thickness of the flange, and then Py. Py is the strength of the steel in Newton per millimeter square. So we have 275. So the thickness is less or equal to 16 millimeter. So you have 265. The thickness of the flange is less or equal to 40 millimeters. You have 255. The thickness of the flange is less or equal to 63. Then we have 245. The thickness of the flange is less or equal to 100. So this applies to grade 40, 43, 50, and 55. And then the modular of elasticity, which is E, or the Young's modular, E, for deflection purposes may be taken as 205 kilonewton per millimeter square for all grades. You have seen this in my previous explanation. So 205 kilonewton per millimeter square is taken as E for all grade stresses. Now let's talk about this section of a steel. So this is the property of a section of a steel. So B is the width of the section. D, capital D, is the depth of the section. Small t is the thickness of the web. And then capital T is the thickness of the flange. And then D, small d, is the depth between fillet. So that is all about the properties of a section of a steel. So the serial size of a universal beam, UB, is given in depth times width times mass. This is kilogram per meter. So for example, 457 is the depth, 152 is the width, and 82 is kilogram per meter. So we have the design consideration, we have the bending, shear, So bending is the ultimate limit state. Shear also is the ultimate limit state. Deflection is the serviceability limit state. Web buckling is the serviceability limit state. And web bearing resistance is the serviceability limit test. So I will discuss each one of these in detail. So I will begin by number one is bending. So the bending is given by the following formula. So it's given by the following formula. So this one is equal to, so MR is equal to FZ, whereby MR is equal to moment of resistance, MU, and F is equal to permissible stress in steel, and Z is equal to section modulus of steel. So I want to show you how I have arrived on this formula. So we know that the bending moment theory formula is given by M over I is equal to F over Y. M over I is equal to F over Y, whereby M is the bending moment, I is the second moment of inertia, and F is the extreme fiber stress in the section, and Y is the distance from the center of the section to the extreme fiber. So if I cross multiply, I will get My is equal to Fi. Then I divide both sides by y. So I will end up having M is equal to Fi over y. So I can separate these two, F and I, so that I can have M is equal to Fi over y. But Z is equal to BD cubed over 12 divided by D over 2, whereby this D over 2 is the Y, and then the BD cubed is I. So the formula will be M is equal to FZ. So MR is equal to FZ. So this is the formula, like that. So for a lateral restraint beam, you can say that for a lateral restraint beam, mu is equal to py sx, where mu is equal to ultimate moment py is equal to design strength of steel. Sx is equal to plastic modulus of section about the major axis obtained from section table from section tables. So in short, Sx is equal to mu over py. From this formula, you can make Sx the subject of the formula by dividing both sides by Sx. Also here it's Sx. So we'll end up having this final formula. Now, after calculating Sx, you will obtain or you select appropriate section from the table from tables like that. So the value here will help you to select appropriate section of steel from tables. Then we'll say BS 5950 places a limit on the moment capacity so BS 5950 places a limit on the moment capacity so that moment capacity X is equal to PYSX is less than PYZX, whereby MCX is equal to applied moment. You'll see this later in our coming examples. This is along major axis. Like that. So Zx is equal to elastic modulus about the major axis. About the major axis. So the suitability of a particular steel beam will be checked by ensuring that the moment capacity mcx of the section is equal or greater than the applied ultimate moment mu. So mcx is greater than or equal to mu. So strength classification, local buckling may be avoided by reducing the stress capacity of the section. So there are 4 classes of sections. We have class 1, which is plastic. Class 2, it is a compact. Class 3 is semi-compact. Then class 4 is slender. So beam cross-sectional classification, this is the beam cross-sectional classification. So we have the limiting proportion and the plastic, compact, and the semi-compact. So this is B over T, this is D over T. So this is 9.0 E, 10 E, 15 E, 80 E, 100 E, 120 E. So for grade 43 steel, so this symbol is for it represents the strain. So this is given by the square root of 275 over Py. So is equal to 2 square root of 275 over Py. So Py is the strength of the steel. We'll see it in our coming example. Now, for design consideration, I have covered only bending. So this one done. So I'm remaining with shear, not covered. Also buckling and web bearing. Also not covered. So I want now to do the summary of design process, and in this I will include the remaining 3 design consideration. So we begin. Summary of the design process. Number 1, determine the ultimate load from the ultimate limit state load, which is given by this formula. This is 1.4 GK plus 1.6 QK, whereby QK is equal to imposed load and the GK is equal to dead load. Then determination of shear force, which is Fv, and bending moment at critical points of the element using the ultimate limit state load. Then number 2, selection of universal beam, which is UB, and the moment capacity of the section MC should be greater than the design moment M. The moment capacity of the section MC should be greater than the design moment M, like that. The moment capacity for the universal beam MC is given by this formula. So the moment capacity MC is given by this formula, whereby Py is equal to the design strength, which is 275 Newton per millimeter square for grade 43 steel. So Sx is the plastic modulus. So the plastic modulus Sx is given by M over Py, where M is the design moment, like that. To select the universal beam section from steel table, so this SX will help you to select the universal beam section from steel tables. The plastic modulus of the section selected should be slightly greater than the calculated. So the plastic modulus should be greater than the calculated plastic modulus. So number 3, you have classification of section. Number 1, you have strength classification. By referring the flange thickness T from the steel table, the design strength can be obtained from table 6 of BS 5950. So number 2, we have section classification. The section classification, so the section is classified as either, number 1, you have the class 1, which is plastic. Then number 2, you have class 2, which is compact. Then class 3, it is semi-compact. And then class 4, slender. So let's now talk about the number 4, which is check for shear. So according to clause 4.2.3 of BS 5950, the shear force, which is FV, should not exceed the shear capacity of the section, PV. So shear force should not exceed the shear capacity of the section, which is PV. So PV is given by this formula, which is 0.6 PY AV, whereby PY is the strength of the steel and AV is equal to D times T, where D is from here to this point, the depth section, and the T, this T is the web thickness, and the shaded area is the shear area. So this shaded area is the shear area, which is given by D times T. And then this distance from here to here is the small d. So the clause also states that when the buckling ratio D over T of the web exceeds this value, then the web should be additionally checked for shear buckling. If the shear FV is less than 0.6 PV, then this is a low shear load. So if FV is less than 0.6 PV, this is a low shear load. So if FV is greater than 0.6 PV but less than PV, then it is a high shear load. When the shear load is a low moment, when the shear load is low, the moment capacity of the section MC is calculated as, so MC is equal to PYSX, but when it is less, it is calculated using this formula, whereby ZX is the section modulus. No, ZX is the elastic modulus. So we now go for number 5, which is check deflection. Check for deflection. Now we have number 5, check deflection. A check should be carried out on the maximum deflection of the beam due to unfactored imposed load, which is 1.0 QK at serviceability limit state. The calculated or induced deflection should not exceed the limit on beams due to unfactored imposed load based on table 5 of BS 5950. So this is table 5. So you have the limit and we have the type of beam. So for cantilever, it is span over 180. Beams carrying plaster or other brittle finishes is span over 360. And then all other beams is span over 200. So deflection formulas of standard cases. We have number one. Number one is a simply supported beam with a UDL. This is W in kilonewton per meter. And this is the distance between the two supports, which is L. So the formula is 5WL square over 384 EI. So we have case number two is a simply supported beam with a concentric load in kilonewton. So the load is at the center of this simply supported beam. So this is L over 2, and then the overall length is L. So the deflection is given by WL cubed over 48 EI. And then we have case number 3 is a cantilever beam. This is a beam supported on one side. No, it's a beam which is permanently fixed at one side and hanging on the other side. So it has a point load on the far end, which is W in kilonewton. So the formula is given by deflection is given by WL cubed over 3 EI. And then we have the last one, which is a cantilever with a UDL. So the formula for deflection is given by WL raised power 4 over 8 EI. Now let's talk about check for web buckling. So what is buckling? Buckling is a failure which occur in a slender column, and it is due to excessive compressive forces which causes the column to bend or buckle in this manner. So this is the section of a column. So this one and this one, as you can see, this is the buckling of this column or I section due to excessive compressive forces. So the figure above illustrates how the load is transmitted through the web at the support, or intermediate position. So the critical point will be at the center of the web, where the maximum buckling moment will occur. According to class 4.5.1 BS 5950, the buckling resistance of unstiffened web is given by PW is equal to B1 plus N1 times T times PC, whereby B1 is equal to stiff bearing length support and N1 is equal to D over 2. So PC is equal to buckling compressive strength from the table 27C of BS 5950. So I will write the statement for you to see it, but this is how the effect or the load from the column will be transferred in this section. So it will be transferred at 45 degree, also at 45 degree, and this is the force from the web. So this will be transferred also at 45 degree. So this distance from here to here is B1 plus N1, and then from here to here is B1, from here to here is N1. So this is the statement concerning the figure I have shown you. So the figure above illustrates how the load is transmitted through the web at the support or intermediate position. So the critical point will be at the center of the web, where the maximum buckling moment will occur. According to class 4.5.1 of BS 5950, The buckling resistance of an unstiffened web is given by PW is equal to B1 plus N1 into bracket times T times PC, where B1 is equal to stiff bearing length for support and N1 is D over 2. So PC is equal to buckling compressive strength from table 27C of BS 5950. Now to conclude, check for web buckling. For entry to table, the value of Py and slenderness ratio. So slenderness ratio is given by 2.5 D over T is used to determine the value of PC, whereby T is the web thickness. So that is the end of check for web buckling. Now we proceed to the last one, which is web bearing. Now let's talk about the web bearing, which is the last design consideration. So this is the section. So we have the root radius. This one is the root radius. Also this one and this one. So this distance is r, is the radius, the root radius, and t is the thickness of this section. So the effective contact is given by 2 into bracket r plus t. And then this is the reaction from the bearing, and it distributes the load at 45 degree. So this distance from here to here is B1, and then here to here is N2. So clause 4.5.3 of BS 5950 show that the bearing resistance is equal to B1 plus N2 T times PYW, where B1 is equal to stiff bearing length and 2 is 2.5 into bracket T plus R. T is the web thickness, and then PYW is the design strength of the web, which is PY. And we end there for today, and that marks the end of the introduction to design of steel to BS 5950. So you will understand better when I will be tackling more examples concerning all what we have covered. So just want you to stay tuned for more examples from design of steel to BS 5950. So my next session, I will start tackling examples. So I will begin by example number 1 as we proceed forward. So let's meet in my next session. So for those who have not subscribed to the channel, I do encourage you to subscribe and be a member. Hit the notification bell so that you may be the first person to be notified. Thank you for your time.